All right, so for today, we're going to talk about more differentiation rules, or more differentiation rules, sorry. Okay, so what if we take the derivative of f of x times g of x, okay? This is not equal, okay? So don't do this, all right? This is not equal to f prime of x times g prime of x. It is not, okay? So I'm going to put arrows here to show you not equal to, right? Don't do this. And I never used to see students do this. And over the last couple of years, I see more and more students do this, okay? Just don't. It doesn't work. It never will work. It just doesn't work, okay? I can't make it any clearer than that. It doesn't work. All right. Let's so what does it equal? Now we're gonna have to go to the limit process, and then we'll never have to do it again, okay? So let's talk about it. So what this does equal when you find the derivative is this. It's f prime of x, so the derivative of the first function, times the second function, and then plus the first function, f of x, times the derivative of the second function, g prime of x, okay? So derivative of first, I'm going to write this, derivative of first times the second function. And when I say first, I mean the first function. And when I say second, I mean the second function, okay? So derivative of first function plus the first function times the derivative of the second function, okay? Now, why does this work? Okay, so I'm going to do a proof and show you where this comes from. So it actually comes from the derivative with respect to x of f of x times g of x. Okay, and this has to do with what you're going to be tested on, okay? I mean, I'm not going to test you on this proof, okay? But I am going to show you like where this comes from. Okay, so here we go. Definition of derivative is the limit as h approaches 0 of f of, so this is the function f of x g of x that we're taking the derivative of. So it becomes f of x plus h, g of x plus h. So we're putting x plus h into this function, and then minus f of x, g of x, all over h. All right, so where do you go from here? Now, I wouldn't expect you guys to see this, okay, but I'm going to add and take away because it'll help us understand where this comes from, okay? Now, I'm going to say this. I've had several students, as they go away to college, they don't like watching this, okay? They don't like seeing this. They just want to get to the problems, right? But when they go back, they go, oh, okay, it really helps you to have a deep understanding by going over this stuff, okay? So this is equal to the limit as h approaches 0 of f of x plus h, g of x plus h. Okay, and then what I'm going to do is I'm going to remove f of x, g of x plus h, but I'm also going to add it. So plus f of x, g of x plus h minus f of x, g of x, all over h, big long fraction bar, right? Now, why? Okay, so why did I pick this? Okay, you're not going to see until just a little bit, and you're going to understand why I picked that. But I want you to understand, this is what's important, is this is the same as the line above it, right? Because all I did was I added, and I subtracted the same thing. So really, it's still this. It just gives me some stuff that I need, okay? And you're going to see in a minute why I needed that, okay? All right, so now one other thing that I'm going to do is I'm going to break this into two pieces. So I'm going to take this piece and this piece, and I'm going to put brackets around it, and I'm also going to put brackets around this. Okay? So what that's going to allow me to do is break this into two fractions. Okay, so this is going to be the numerator, plus this is going to be a numerator, and the common denominator is going to be h. You're not going to know why right now, okay? This took somebody that really smart to figure this out, okay? It wasn't your teacher, all right? So the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x plus h, over h. And really, we should have a big bracket because we're taking the limit of the whole thing here. And then plus f of x, g of x plus h, minus f of x, g of x, all over h. All right. Now, here's why I picked this. This has something in common. These two have something in common, and it's this g of x plus h, which means I can factor it out of this. So this becomes the limit as h approaches 0 of f of x plus h minus f of x over h, and then times g of x plus h. And then plus, okay, so out of this one, so I factored out of the back, this one has something in common too. And what it has in common is this f of x. Now I'm going to take this one and factor out into the front. So plus f of x times g of x plus h minus g of x over h. Okay, now when we take the limit of a sum, so right here's my sum, I can take the limit of each one of these. So this becomes the limit as h approaches 0 of f of x plus h minus f of x over h times g of x plus h plus the limit as h approaches 0 of f of x times the fraction g of x plus h minus g of x over h. Okay, now the limit of a product, and we have a product here, is we can take the limit of each one and get the result of that. So this becomes the limit as h approaches 0 of f of x plus h minus f of x over h times the limit as h approaches 0 of g of x plus h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x over h. And we should recognize what the heck this is. And that is the definition of the derivative of f right there. Okay, so this winds up being, that's the same as f prime of x. So that's where we get the f prime of x. And then times, and as h approaches 0, well, this just becomes g of x. So times g of x. And plus, okay, so limit as h approaches 0 of just plain old f of x, well, that's just f of x times, and then we should recognize this, oh, this is the derivative of the g function. So this becomes g prime of x, okay? And that's why this works. So it's the derivative of the first function times the second function plus the first function times the derivative of the second function, okay? So we went through the limit process, and now we never, the beauty of this is we never have to do this again, because this is true, and it's always true, So we never have to go through this again when we have a product of two things. It's always going to be this. Okay? All right. So let me go and let's do some problems now using this is called the product rule. Okay? So here's a problem that you could, because it's a quadratic here and a linear here, you could just multiply this out, and that would be an option. Okay, you could multiply it out and then get the derivative, and you wouldn't have to use a product rule. Okay, so this is one example that we're going to use a product rule, but you really wouldn't have to use a product rule. We could just use some algebra and then find the derivative of that. Okay. So we do need the product rule, especially when we start multiplying, like it's called a transcendental function, like the trig functions or the logarithm functions times like a polynomial. We have to use the product rule when we come across those. Okay, so we got to know it. So this right here is we're going to call that one my first function, so f of x, and I'm going to call this one g of x. All right. And so h prime of x is equal to, okay, so it'd be the derivative of this first function, right? So this would be, in parentheses, we'd write 3 and then minus, and then we're going to bring the power down, so that'd be 2 times 2, which is 4 times x. So minus 4x times the second function left alone, so that'd be 5 plus 4x. And then plus, and then the first function left alone, so 3x minus 2x squared, and then times the derivative of this second function. So the derivative of 5 would just be 0, and plus, so 0 plus 4, right? So this just be times 4. Okay, now I'm going to multiply this out. You wouldn't have to. This is the derivative. You're done with calculus. Okay, now it's just algebra. Okay, so h prime of x, if we multiply this out, this would give us 15 plus 12x minus 20x minus 16x squared. And then we could distribute the 4 here, and that makes 12x, so plus 12x. And then minus 8x squared. And really, I didn't need this parenthesis. I was going to use it, and then I wound up not. Okay. So combining like terms, this would be negative 16x squared and negative 8x squared. So that makes negative 24x squared. And then we have a 12x and a 12x, which makes, no, I'm sorry, a 12x and a negative 20x and a 12x. So the 12x and 12x makes 24x minus 20x would be 4x. And then we have the 15. I think that's the only constant. Yeah, so plus 15. Okay, so I want to show you, okay, what if we had multiplied this out? Okay, so if we had multiplied it out, h of x would have become 15x plus 12x squared. And then minus 10x squared. And then minus 8x cubed. Okay, so cleaning this up. All right, we'd have negative 8x cubed and plus 2x squared and then plus 15x. Okay, so now we could take the derivative of it. So h prime of x would be negative 24x squared plus the 4x and then plus 15, and see how we get the same thing. Okay, so 2 different ways of doing the problem. Okay, I wouldn't be upset if you, unless I tell you use a product rule. Okay, I wouldn't be upset if you went with this route. Okay, just depends on the problem. All right, and if you did take the derivative of this and times this, let's do that. Let's show what happens. Let's show why this doesn't work. Okay. All right. So you think h prime of x, what if we take the derivative of this? Well, that would be 3, right? Minus 4x, and then times, and the derivative of this, well, the derivative of 5 is 0, and the derivative of 4x would be 4, so this would be times 4. See what happens we get? We would get h prime of x is equal to 4 times 3, which is 12 minus 16x. See, we don't get the right thing, right? Okay, we don't get the right thing, right? Okay, so this is what we would get if we took the derivative of the first times the derivative of the second. This is what we get, and it's not correct, right? It doesn't give you the same thing. Now, if you do it right, regardless of which method you use, look, we get the same answer, which means this does not work. Please do not take the derivative of the first times the derivative of the second. It does not work, okay? All right, so that's how you do product rule. All right. All right. So now we're going to take a look at what the quotient rule is. Okay. And I want to point out once again, this is a not equal, right? Okay. So the derivative of f of x over g of x does not equal f prime of x over g prime of x. It does not work. Don't do this. Okay. So what is it then? Okay. And I'm just gonna write it out for you, and I'm gonna show you where it comes from again. Okay. So the derivative with respect to x of two functions that you're dividing, it winds up being the derivative of the top function times the bottom function minus, so it's going to be changed to minus, and it's going to be the top function times the derivative of the bottom function, so times g prime of x, all over, and it would be the bottom function squared. So g of x squared. All right, now, I want to show you where this comes from, but I write this different calculus teachers teach this differently, okay? Because they may put g of x first because they like the g of x and then f prime of x, okay? But regardless, it will give you the right answer, okay? You could only switch these two. You couldn't switch these, all right? Because subtraction, the order matters, okay? And I try to write this so it's easier to remember. I write this I write it this way because it looks just like the product rule, right? But instead of the first function, we say the top function, okay? And instead of the second function, we say the bottom function, okay? So the derivative of the top function times the bottom function minus the top function left alone times the derivative of the bottom function all over the bottom function squared. Okay, so why does this work? Okay, so we've got to go back to the limit, the definition of what a derivative is, okay? All right, this is going to take a little bit of work, a little bit more work than the product rule, okay? So d dx, so put your boots on and we're going to go for it, okay? So d over dx of f of x over g of x is equal to, and this becomes a limit, the limit as h approaches 0 of, we're going to put x plus h into this function, so it's going to be f of x plus h over g of x plus h minus the function all by itself, which is f of x over g of x, all over h. All right, now what I'm going to do is I'm going to multiply the top of this fraction and the bottom of this fraction by, okay, g of x times g prime of x, because we have a complex fraction right now. Okay, so this becomes the limit as h approaches 0 of, and when I multiply this, it becomes f of x plus h times g of x. And then minus, when I multiply this one by the g of x times g of x plus h, what the g of x's are going to cancel, and I'm left with minus f of x g of x plus h. Over, and the bottom becomes h times the g of x times the g of x plus h. Okay, so now once again, you're starting to see in this, like this is where you get the g of x squared, right? Because if the limit as h approaches 0, that's going to become 0, right? The only thing is we got to get rid of this h, okay? So right now it won't work, but you can start to see the g of x squared right here starting to appear already, okay? All right, so what I need to do to this one, I need to, in the numerator, I need to add and subtract like I did before, okay? So this winds up being the limit as h approaches 0 of f of x plus h, g of x. And what I'm going to do is I'm going to subtract f of x, g of x, but I'm also going to add f of x, g of x, and then minus, and we still have this, f of x, g of x plus h. All over, and then h times g of x times g of x plus h. Okay, now, a couple things that I'm going to do is I'm going to separate this again like I did before, okay? But it's going to be a little bit different. I'm going to put these two together, and I'm going to add this. So I'm grouping stuff together, okay? All right. Now, how do I get rid of this h right here? Okay. And also I need an h up in here because look, we have some derivatives up here, right? So we got to get the h up here. So the way I'm going to do that is I'm going to multiply this by 1 over h over 1 over h. Because when I take 1 over h and multiply it by this h, they're going to cancel each other out, and I'd be left with g of x times g of x plus h, and it's start to see, okay, that's where I'm going to get the g of x squared, okay? All right, and the other thing is I'm going to put this first grouping over h because I need to distribute this because this is a sum right here. So I'm going to multiply this by 1 over h, and I'm going to multiply this by 1 over h, okay? So that makes this become the limit as h approaches 0 of, and I'm going to put this one over the h, so f of x plus h g of x minus f of x g of x over h, and then plus, and then f of x g of x minus f of x g of x plus h over h. And then because I need to distribute that with this and with this, okay, all over, and this just becomes g of x times g of x plus h. Okay, so do you see something right here that we could pull out? And it would be the g of x, okay? So this becomes the limit. I'm going to slide it up so we don't lose it. The limit as h approaches 0 of f of x plus h minus f of x over h times g of x. Now, this is going to be the weird part, okay? Over here, I need this to be subtraction, right? So what I'm going to do is I'm going to factor out a negative. Now, what's that going to do is it's going to change the sign of this. And so this one's going to become positive, and now this one's going to become negative. And I'm going to write this one first, okay? So it's minus, and then I have f of x, g of x plus h. And this one that's positive now becomes minus, and f of x, g of x, all over h, all that over g of x times g of x plus h. Okay, so we factored the g of x out of this one, and now we're going to factor an f of x out of this one. So this becomes the limit as h approaches 0 of f of x plus h minus f of x over h times g of x minus, and then out of both these I can factor out an f of x. So f of x times g of x plus h minus g of x all over h all over g of x times g of x plus h. Okay, so now, okay, if to take the limit of a fraction or a quotient, we take the limit of the top over the limit of the bottom, okay? So I'm going to kind of do this in our head, all right? So this, if we take the limit of this top, then I got to, and this difference is the top, right? So I got to take the limit of these two, but to do the limit of these two, I got to do them each one individually, and then minus, and I got to do these two individually, right? So this, you should recognize that's the definition of a derivative. So this first one becomes f prime of x. And if we try to do the limit as h approaches 0 of this one, well, it's just g of x. And then minus, and we take the limit of this one, but I got to take the limit of this one and the limit of this one. Well, the limit of this one is just going to be f of x. This one is the definition of the derivative of g. So that'd be g prime of x all over. Okay, and then as we take the limit as h approaches 0 of this denominator, let me slide it up a little bit before I get to the denominator. This one doesn't change, and this one becomes just g of x because h is approaching 0. So this becomes g of x, and this is g of x, and g of x times g of x is g of x squared. Now, I want to say this. If you're writing g of x notation, okay, you have to use a bracket around it. So you're going to write g of x like this, and then squared. Okay? All right, guys. So that is the proof for the quotient rule. Now, what's beautiful about this is I never have to do this silly stuff again, okay? And then we're done. All right, so for this first problem, there's no other way to do this other than using the quotient rule, okay? So how do we find, if y equals 5x plus 2 over x squared plus 1, how do you find dy over dx? Well, we have to use this quotient rule, okay? So dy over dx is equal to the derivative of the top. So the derivative of 5x plus 2 would be 5 plus 0, so that'd just be 5, times the bottom, which is x squared plus 1, and then minus, and then the top function, which is 5x plus 2, times the derivative of the bottom. Well, the derivative of x squared would be 2x, and then plus 0, so 2x, all over, and then x squared plus 1, and then we would need to square this. So it becomes x squared plus 1 squared. Okay, cleaning this up a little bit. Okay, so dy over dx is equal to, this would be 5x squared plus 5. And you need to think of this, okay, I'm going to distribute this 2x, but you can also think of, okay, I'm going to distribute negative 2x. So negative 2x times 5x is negative 10x squared, so minus 10x squared. And negative 2x times 2 is negative 4x. All over. Okay, and let me say this. You never want to expand this one out. Just leave it like this, okay? So this becomes x squared plus 1 squared. And I should have said this. This is the derivative right here. From here on, it's just cleaning it up using algebra. So then dy over dx is equal to, so this 5x squared minus the 10x squared makes negative 5x squared. And then we have minus the 4x. And then plus the 5. All over, and this is x squared plus 1 squared. And that's the derivative. That's as far as you can go, okay? You don't want to leave it like this. And there's reasons why for later on that we're going to do that you want to actually multiply it out, okay? Because sometimes what we're going to want to do is we're going to want to factor this, and we're in the future we're going to need to figure out where the denominator winds up being 0 and where the denominator winds up being 0. And with the subtraction in here and this, we have a product, right? We're subtracting products, so it's you really can't figure it out that way. All right, so you have to clean it up. All right. Okay, so let's go on to the next problem. So I want to talk about this problem, okay? There's a couple ways you could do this, okay? And then I'm going to do it one way. It's not better, it's not worse. It's just one way of doing it. And I'm probably going to pick a little more complicated way than maybe you would do. Either way is going to be fine. Before we take the derivative on this, okay, one thing that you could do, because if you notice, we have a complex fraction, right? And so what you could do to get rid of the complex fraction is we can multiply by x over x. And so this would be 3x minus 1. That's what the top would become. And the bottom would become x squared plus 5x. And then you could take the derivative there. And if you did it that way, I'm happy, okay? I want you to know I'm happy. I'm good with that. You don't have to do it the way I'm going to show you, okay? So there's just alternatives of doing things. That's what I want to point out, okay? So another way of looking at this problem is I'm going to rewrite this with a negative exponent because 1 over x really means x to the negative 1. So this is 3 minus x to the negative 1 power over x plus 5. And that's the way I got rid of the complex fraction, okay? So now, what do we get for a derivative? So f prime of x. Well, we got to take the derivative of this top function. And the top function, the derivative of 3 is just 0. And so we have a minus, or we can think of this as being negative. A negative times a negative is going to be a positive. And we got to subtract 1 from this power. So that's going to be positive x to the negative 2, or just x to the negative 2, times the bottom, which would be x plus 5, minus the top, which is 3 minus x to the negative 1 power, times, and then the derivative of the bottom would just be 1, all over the bottom squared. So x plus 5 squared. Okay, so now I need to multiply this out, and I need to multiply this out. Okay, and so what we would get here is, this is a power of 1, so we need to add them. That's one of the reasons I chose to do this, because I want to practice our exponent rules, okay? So x to the negative 2 and x to the first becomes x to the negative 1. And then x to the negative 2 times 5 would be plus 5x to the negative 2. And really, I just need to distribute this negative, so minus 3 and then plus x to the negative 1, all over x plus 5 squared. Okay, so we can do some combining here because we have one of these x to the negative ones, and we have another one here. So that makes this derivative become 5x to the negative 2 plus 2x to the negative 1 minus 3 all over x plus 5 squared. Okay, so we don't want any answer with negative exponents, okay? We want positive exponents, okay? So what does x to the negative 2 mean? It means 1 over x squared. So this becomes 5 over x squared. And then plus, and this is 1 over x, so this becomes plus 2 over x. And then minus 3 all over x plus 5 squared. Okay, now what we're going to do is we're going to multiply the top and bottom. We're going to clear out this complex fraction now. Now's the time that I'm going to do it, okay? So times x squared over x squared. So that makes this derivative, if we distribute this x squared, that makes this 5. And then plus 2x squared over x, which makes plus 2x. And then minus 3x squared. over x squared times x plus 5 squared, which winds up being negative 3x squared plus 2x plus 5 over x squared times x plus 5 squared. Now, and that's your final answer right there. Okay, so I'm gonna say this. If you had gotten rid of the complex fraction first, you would have made your derivative way, way easier. Like this would have been easier than what I did in the derivative part, okay? But if you were to go to solve it, it would have actually made the problem harder. So the route you take can make one part easy and then another part hard. So if I was trying to figure out where the denominator was 0, this is going to be easy to figure out. It's going to be x equals 0 and x equals negative 5. Bam, that's easy, okay? This one doesn't factor nicely, okay? But if we were able to, like, we would try to factor this and then set each factor equal to 0, okay? But you're going to have a very, very difficult time if you multiply this by x over x, and the derivative would be easy. The derivative would be easy. It would be easier than the way I did it, okay? But when you go to solve it, you would wind up having x, you would have a, you would have x squared plus 5x inside a squaring function. So it would make it a little bit harder to solve, okay? And that's my point. That's why I chose the way I did it, because I know what's coming, all right? And so, not that you have to do this way. If you get the right derivative, you have the right derivative, okay? I'll count it right, okay? All right, let's look at another problem. Okay, so for this one, it looks like a quotient. It looks like what we just did, right? Yeah, it looks just like what we did. Quotient rule, right? No, it's actually easier than that because we're dividing by a constant right here. There's an easier way to do this, okay? So you don't, I've said this to people in the, well, classes in the past. It's easier to say it in class than online than doing it right now, but it's like this. You're trying to take a shotgun to kill a fly. If you try to use a product rule on this, you're using a shotgun to kill a fly. Like, you're killing everything. Like, you're blowing holes in everything, right? You don't want to do that. You want to pick something easier. Yeah, that shotgun might kill a fly, but you're going to do damage to your house, okay? So, all right, I'll calm down now, all right? So what I want you to understand is this. This is just dividing this by 6, right? So this is 1/6 x squared. We can rewrite this and it's going to be way easier. So you want to look for easier ways of doing things. So this would be 1/6 x squared plus 3/6 x. All right, now 3/6, I'd want you to reduce that, okay? So this becomes y is equal to 1/6 x squared plus, and 3/6 becomes 1/2 x. So what does dy over dx become? Well, it'd be 1/6, because that's a constant, times 2x, right? Because the power down, subtract 1 from the power, and then plus, and then power down, 1/2 times 1 would be 1/2, and then this becomes x to the 0, which is just 1, so it's just going to be plus 1/2. Okay, so this becomes 2/6, which is 1/3, and dy over dx is equal to 1/3 x plus 1/2, and it's as simple as that. Okay, so don't use the quotient rule when you're dividing by a constant like 6. Also, I should say this: don't use the product rule when you're multiplying, something like this. F of x is equal to 6 times x squared. Okay, don't use the product rule. That's not, the product rule is not intended for this. Okay, this would just be 12x. That's all it is. Okay, the derivative of fx when f of x is equal to 6 times x squared, it's just 12x. Okay, so it's 6 times the derivative of that. Okay, all right. Now I want to talk about higher order derivatives. Okay, so we can take the first derivative, sure, all right, but we can take higher derivatives, okay? So if we have, and I want to show the notation for this, okay? And let me pause this. Okay, so I'm realizing I am talking way too much to you guys, okay? So here we go. So f of x, all right? The next derivative would be f prime of x. And then we have f double prime of x. And I'm going to say this is where the notation starts to come into, where you start to understand the notation, okay? So this is the first derivative, this is the second derivative, and then we can take the derivative of the second derivative, which becomes the third derivative. And then we can take the derivative of the third derivative, and that would be the fourth derivative. Now, when we get to the fourth derivative, we actually stop writing the apostrophe, okay? So this would be the fourth derivative of x, and we write it like that. So don't write a 4 because that means something different, okay? We put a 4 in parentheses, okay? So if we're using y notation, we could say y, and then y prime for the first derivative, and then y double prime for the second derivative, and y triple prime for the third derivative, and then we write y, and it almost looks like an exponent, and that's why we want to put parentheses around it, because when you put parentheses around it, everybody knows, oh, that's not an exponent. That actually means derivative, okay? I don't like using this notation for y, okay? Other than maybe y and y double prime and y triple prime, I don't like this because, and here's the rationale, I don't like it because it looks like an exponent, okay? All right, so there's another notation that I think is better when we use y, okay? So we can take the derivative, the d stands for derivative, with respect to x of y, and that's just dy over dx, okay? And then we can take the derivative with respect to x of this, okay? And now this is where notations, you start to understand the notation, okay? Not the with respect to x. You're gonna understand that later on, okay? Like not this unit that we're in right now, but unit 4, okay? So here we go. So we're gonna take the derivative with respect to x of dy over dx. Okay, so we're taking the derivative with respect to x of this, right? And so the second derivative is written like this. D, and it looks like a square of y over dx times dx. And so we write dx with a little power. And the dx goes together, so that's why we write the 2. The power here too doesn't go with x, it actually goes with the dx. But d and an x like this always go together, okay? It's one thing, and everybody knows that, okay? So how do we find the third derivative? Well, we have to take the derivative with respect to x of this one. So this becomes d dx of the second derivative of y with respect to x for the second time. And so this, and you see how it starts to become, this is d cubed, okay? That's what it looks like. It's really not. It's the third derivative of y. It's third derivative of y with respect to x for the third time, okay? And then the fourth derivative would be d dx, the third derivative of y over dx, third derivative with respect to x for the third time. And so this becomes the fourth derivative of y with respect to x for the fourth time, okay? And that's where you start to understand the d over dx notation, okay? And why we use it, okay? So this means the fourth derivative, okay? You don't want to put the 4 right here on the right side of the y. It's actually after the d, because it's d cubed, looks like d to the fourth, okay? Why would you ever need to take higher derivatives? Glad you asked, okay? So here's why you would need to take it, okay? It actually has to do with physics, and actually what we're talking about in my physics class right now, okay? So here we go. If y equals, and I'm going to write this, y is equal to x cubed minus 5x squared plus 2, okay, then the first derivative, so the derivative of y with respect to x for the first time, winds up being 3x squared minus 10x plus 0, okay? Taking the derivative with respect to x a second time on this would be the second derivative of y with respect to x for the second time. And that would come out to be 3 times 2, which is 6, 6x minus 10. Taking the derivative taking the derivative of y with respect to x for a third time becomes the third derivative of y with respect to x for the third time winds up being just 6. And now what we can do is take the derivative of this, so the fourth derivative, so the fourth derivative of y with respect to x for the fourth time, and the derivative of 6 would be 0. Okay, so how is all this stuff related to each other, okay? So if you took physics, all right, or you are taking physics, all right, this is the position function. This right here is the velocity function. And some of you were saying, Mr. Mitchell, these derivative graphs, they look like velocity graphs that we did in physics last year. Yeah, it's because that's what it is. The first derivative of something is the velocity. The next derivative, so the derivative of velocity is acceleration. Okay, so Mr. Jet talked about position, velocity, and acceleration, and all had to do with slope, right? The slope of position is velocity. If you look at a velocity function and find the slope, that would be acceleration. Remember doing all that? Okay. And there's even more. There's more to it than just acceleration. So there's one more function. Okay, you only learned this from Mr. Jet never taught this. Okay, but if you look at the change, if you look at an acceleration graph. All right. And Mr. Jet never talked about this because in physics and in the physics even that I teach, the acceleration is always a constant. Okay. So you need calculus to do further stuff. Okay. So when the acceleration starts to change, we need calculus. And so this function right here, the name of it it's called the jerk function. So I wish you guys were in class. Okay. Because we joke about this all the time. But if you look at this, okay, it's when you feel the jerk in your car, like when you take off really fast and the acceleration is really changing fast, that's the jerk you feel in your car, okay? And then for this jerk, if we take one more derivative, it's called the snap function. And they really need the snap function in like when they're doing robotics and things are moving quickly, they gotta do smooth transitions. And so like it looks more natural instead of, slamming into stuff and robotics really moving fast and then stopping really fast. That's why they need this type of function. Okay. All right. So position, velocity, acceleration, jerk, and snap. And actually there's a fifth derivative, and the fifth derivative is crackle. And the sixth derivative is pop. I'm not lying to you. It's snap, crackle, pop. So funny. This one's called jerk because you feel a jerk when you in your car. If you ever feel like you're jerked in your car, that's this. What you're feeling is a change in acceleration. Okay? All right, guys. That's it for today. That was a long lesson. I should have warned you guys up front. Okay. All right. That's it, guys.